Hello and welcome to Algebra 2 tutorial. In this video we are still looking at polynomials and we're going to focus on finding their x-intercepts. And so remember, x-intercepts could also be called roots, zeros, or solutions, and we want to find those for our polynomials. Now, we kind of already have one strategy to do this. If our equation is in factored form, this is actually really easy. So let me show you how that works. So here we have an equation in factored form. And because x-intercepts are also zeros, we just figure out what makes each of these equal to 0. And we know x equals -2, x equals 3, and x equals 6 are all going to be x-intercepts. And we can check that. I've got a graph for us right here. -2 is an x-intercept, 3 and 6 are also. And so you can see that's very easy if you have the equation in factored form. And in the previous videos, we had a strategy for taking a polynomial and putting it in factored form. Sometimes we actually can do that and then find the x-intercepts fairly easily. Sadly, oftentimes that is not the case, and we don't have our equation in factored form. So we need something else. So in this video, we're going to take a look at that something else. How can we find the x-intercepts when we can't take our polynomial and put it in factored form? Well, that something else is called the rational root theorem. It allows us to find the possible roots, or x-intercepts, from a polynomial in standard form. So let's take a look at how that works. So first, sort of the background information about where the rational root theorem comes from and why it works the way it does. So to do that, we're going to start with the answer. So here we have a nice, easy polynomial, but it's in factored form. So we can find the x-intercepts really easily. Usually, however, you will get this in standard form. So let's get standard form. 2x times x is 2x squared. Times -5 is -10x, plus 1x, minus 5. And so the problem you would usually get is 2x squared minus 9x minus 5. So usually that's the equation you would get. Now yes, we can factor this equation pretty easily and get back to here, but let's pretend that we can't. The rational root theorem says that your x-intercepts will be fractions where the top of the fraction is one of the factors of this number, so 5 and 1, and the bottom of your fraction is one of the factors of this number, so 2 and 1. So remember, this is the top, and this is the bottom. So those possibilities would be 5 on top, and then you could have either 2 or a 1 on the bottom. So a 2 or a 1. And then this one, or we did the 5, now the 1. So the 1 can be on top, and either the 2 on bottom or another 1 on the bottom. But we don't know whether they're positive or negative, so we have to put a plus or minus in front of each one because they could be positive or negative. We don't know. And it says the x-intercepts, if they exist, and they're rational numbers, meaning they're fractions, it has to be one of these. All right, now, where does that come from? Why does it have to be one of these? Let me try to explain that to you. We're going to go back to our answer to show you why. So if you have a nice easy one right here, x minus 5, we know to make that equal to 0, x has to be 5. Now where did that 5 come from? Well, you multiply the last two numbers 1 times the 5, then it always gives you this ending number right here. And so this answer right here, 5, is hidden inside of this 5. Now we don't know if it's the 5 or the 1, which is why we have to do both. So if you have a nice easy x-intercept, it is going to be hidden inside this last number. And technically there is a 1 right here, and so you would have another step, divide by 1. And so technically it's a 5 over 1, and you can see it pops up right there. Now let's do the other one so you can see that one more time. So let's do this one. 2x plus 1 is equal to 0. Now to solve that, we minus 1 to both sides. 2x is equal to negative 1. Divide by 2 on both sides. X equals negative 1/2. So where does this answer sort of come from? Well, it started with this 1. And where did that 1 come from? Right here. And that 1 times the 5 is also hidden inside this 5 right here. And so the top number, the 1, is also inside this back final number, which happens to be a 5 this time. All right, what about the bottom number, the 2? Where did the 2 come from? Well, the 2 was in front. All right, and what happens to that front number? Well, the front multiplies the front, the other x, and it becomes the first term. And so inside this first term is hidden that number that we always divide by at the end. Here we divided by 1 just to see it, we didn't have to, and here we had to divide by the 2, and so that bottom number will always be hidden inside the front number. So that kind of tells you a little bit why we're using the first and the last number, and why this one always has to be the top, and why this one always has to be the bottom. And then you just simply have to try them all, which does get a little tedious, but it does work. So let's take a look at another example here. But first, just to recap, the rational root theorem is helping us find these x-intercepts. So let's find some x-intercepts of a nice complicated example. So again, if we're going to have any x-intercepts here, the top number of that fraction will be hidden inside this 50, and the bottom number will be hidden inside this 3. And we just have to write out all the combinations. So the factors of 50 are 1 and 50, 2 and 25, and 5 and 10. The factors of 3 are just 1 and 3. So our x-intercepts, these are going to be the top numbers, these are the bottom. So 1 over 1 or 1 over 3. That takes care of this one. 2 over 1 or 2 over 3. That takes care of that top number. 5 over 1, 5 over 3. And then 50 over 1 or 50 over 3. 25 over 1, 25 over 3. And our last 10 over 1 or 10 over 3. That gets rid of that one. All right, so we have our possibilities. 1, 2, 3, 4, 5, 6, and 6 is 12. Sadly, I haven't put in the plus or minus yet. We don't know whether they are positive or negative. So instead of 12, we technically have 24 possibilities, and we got to check them all. Just kidding, we're not going to do that. That would take way too long. Let's pick one and try it out. So let's pick positive 1 and see if positive 1 works. Now, yes, we could just plug it in, but that's kind of difficult. We actually have a tool that does this very easily. It's called synthetic division. If we think that positive 1 is an x-intercept, that means x minus 1 is a factor. And if it's a factor, we can divide by it. So we're just going to divide by x minus 1. You might groan a little bit if you remember division, but synthetic division was really easy when the thing you're dividing by is simple, and this definitely meets that definition. And so we're just going to use synthetic division to test this out. So remember, you don't use the negative 1, you use the positive 1. In synthetic division, you're actually testing the x-intercept. And then we write out the coefficients. And let's see if this works. Bring down the 3. 1 times 3 is 3. That's negative 23. Multiply by 1. Add those together, you get 42. Multiply by 1. And you get negative 8. So there's a remainder, which means we did not divide evenly. So this did not work. So we can cross out positive 1. Only 23 more to go. Yeah, again, we're not going to try all 24, but that shows you how you can check a possibility on a problem like this where there's so many possibilities. Hopefully you get some other information, and that's what I'm going to give you right now. So here is a graph of this polynomial, and with that graph we can eliminate some choices and find a good candidate to test next. So looking at this, we have an x-intercept right here. That's a bit of a decimal. I'm not sure what that is. We also, it looks like we have one right here, right at 2. So that's a good one to try. And we have one right here at 5. So I'd say we want to try those next, a 2 and a 5. So let's try the 2 first. So we're going to check it with synthetic division. Oh wait, I'm going to back up a little bit, give myself some more space. So we're going to try 2 and see if it works. So put the coefficients here, negative 26, 65, and negative 50. So the 3 comes down. 2 times 3 is 6. That's negative 20. That's negative 40. And that is 25. And 2 times 25, look at that, 50. We get a remainder of 0, which means this is one of our x-intercepts. That works out. So we're going to start writing our factored form here. We now know that x minus 2 is a factor. So now we can keep going. We checked 2. The other one we were going to check, I believe, was 5. So let's see if 5 works. So bring down the 3. 5 times 3 is 15. Negative 5. 5 times 5 is negative 25. And yep, that also works and comes out to 0. So 5 is another x-intercept. So that means one of our factors is x minus 5. Now it looks like we could keep going. We only have a little bit left though. So that's our number, remember, and this is our x. And so our last bit of the equation that's left over is 3x minus 5. And so the first two, we have our x-intercepts nice and easy. This one might not be quite as easy. I'll do it down here so I've got some room. 3x minus 5 is equal to 0. Add the 5, divide by the 3, 5/3. So that fraction x-intercept that we saw right here is apparently 5/3. And we found all 3 of them, and we now have our factored form. So that is the rational root theorem. And again, we're all pointing towards our x-intercepts. How can we find the x-intercepts? If you have factored form, you're lucky and it's easy. If you don't have factored form, you need to use the rational root theorem, list out all the possibilities, and then check them using synthetic division. So let me give a problem for you to try. First, list out the possible rational roots, and then test a few possibilities and use the graph to help you figure out which ones are a good idea to test. Good luck.